Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Great to be back. Today, we're really diving deep into something absolutely critical for, well, almost everything electronic these days.
You mean keeping things cool, thermal management, and the fluid mechanics behind it.
Exactly. It's the dual challenge, right?
Mm-hmm.
How electronics generate heat and how we, as engineers, have to design systems, sophisticated systems, sometimes to stop them from melting down.
It's the unsung hero, isn't it? Get it wrong. And performance tanks, or worse, total failure. So our mission today is to unpack this. We're looking at the physics, the key calculations.
Tracking that heat from the tiny silicon chip,
Yeah.
understanding all the barriers it faces, this idea of a thermal resistance network.
And then figuring out the hardware, the pumps, the fans needed to actually move that heat away using fluids. It's quite a journey for that energy.
It really is, from microscale physics to macro-scale machinery.
Okay, so let's start at the source. The heat is generated in the chip. How does it even begin to get out? What are the basic ways heat moves in these systems?
Fundamentally, you've got four modes operating: conduction, convection, phase change, and radiation, often all at once, in series and parallel.
But right at the start, inside the chip package, through the solid materials.
There, it's almost entirely conduction, heat moving through solids.
Okay, and engineers like analogies. Is there a good one here?
Oh, definitely. The electrical analogy is perfect. Think Ohm's law. Temperature difference is like voltage.
Heat flow is like current.
Exactly. And that lets us define thermal resistance, URDE, which behaves just like electrical resistance. It tells you how much temperature push you need for a certain amount of heat flow.
So for a simple block of material, there's an equation for this URD.
Yep, a straightforward one for one-dimensional flow. R sub CD equals L divided by the product of K and A.
Okay, let's break that down. L is the length the heat travels.
Right, K is the material's thermal conductivity, how well it conducts heat. Higher is better.
And A is the cross-sectional area the heat flows through. Bigger area, easier flow.
Precisely. So, shorter path, better material, bigger area, all reduce that basic conduction resistance.
But like you said, it's rarely that simple in a real device. The heat doesn't just flow in a straight line. What happens when, say, heat from a tiny chip needs to get into a much larger heat spreader?
Ah, now you're hitting the complex and often dominant resistances. First is spreading resistance.
Spreading, so the heat spreads out. Shouldn't a bigger area reduce resistance?
You'd think so because A increases, but forcing the heat to flow laterally, sideways, through the material to reach that larger area, that creates its own resistance, an additional penalty.
Okay, so it's the cost of changing direction, essentially.
Kind of, yeah. It's resistance due to the heat flux lines having to bend and spread out. It can be surprisingly significant.
And what about when two different solid parts touch, like the chip touching the heat spreader or the spreader touching the heat sink base?
That's the other big one. Interface resistance or contact resistance. This one. This one can be a real killer.
Why, if they're clamped together tightly?
Because even surfaces that look perfectly smooth are microscopically rough. Think tiny peaks and valleys, asperities.
Right, so they only actually touch at the tips of those peaks.
Exactly. The real solid-to-solid contact area is incredibly small. Most of the interface is actually a tiny gap, usually filled with air.
And air is a terrible conductor of heat.
Awful. So the heat transfer across that interface, the total contact conductance, H sub CO, has two parts. A tiny bit through the solid contact points, H sub C, and the rest try to jump the gap, H sub G.
And that gap part is the problem.
Often the biggest problem in the whole stack. You can have centimeters of copper with less resistance than one poorly managed microscopic interface gap. It highlights why things like thermal paste or interface pads are so critical.
Wow. Okay, so you have the basic conduction resistance, the spreading resistance, the contact resistance. How do we sum this all up for, say, a whole chip package?
We use an overall figure of merit. The total thermal resistance, R sub T, it's usually defined empirically.
Empirically meaning based on measurement.
Yeah. R sub T equals, open parenthesis, T sub J minus T sub FL, close parenthesis, divided by Q sub C.
So the junction temperature, T sub J, minus the coolant fluid temperature, T sub FL, all divided by the chip's heat output, Q sub C, basically degrees C rise per watt.
Exactly. It tells you the total temperature penalty for getting heat from the junction out to the coolant. And it's made up of internal conductive resistances, like we discussed, often lumped as R sub JC.
Plus the external resistance getting heat off the surface, R sub EX.
And sometimes a term for the fluid heating up as it flows, R sub FL. Managing all three is key. You can't just focus on one.
All right, let's move to that external part. 4 sensors. We've conducted the heat to the outside surface, maybe a heat sink. Now we need to get it into the fluid, air, or liquid. That's convection, right?
Correct. Convection is heat transfer from a surface to a moving fluid. The basic relationship is Q equals H times S times the difference T sub S minus T sub FL.
So heat flow, Q equals, that's the heat transfer coefficient.
Big one engineers chase, yeah.
Yeah.
S is the surface area in contact with the fluid.
And T sub S minus T sub FL is the temperature difference driving the heat transfer.
Right. So if we define convective resistance, or CVD, using our electrical analogy again.
It would be the temperature difference divided by the heat flow. So 1 over H times S.
Precisely. Or CV equals 1 divided by the product HS. Simple concept, but maximizing H and S is where the engineering comes in.
Okay, let's take S first. Increasing surface area. That's why we have heat sinks with all those fins, right?
Absolutely. Fins, or extended surfaces, are all about dramatically increasing S, the wetted area, to lower George GVA.
But is it quite that simple? Does a fin work perfectly along its whole length?
No. Good point. The fin itself has internal conduction resistance. Heat flows from the base out towards the tip, and the thin material isn't perfectly conductive.
So the tip of the fin is cooler than the base?
Yes, which means it transfers less heat than if it were at the base temperature. We quantify this using fin efficiency, eta sub F.
Eta sub F, like a percentage.
Yeah. It's the actual heat the fin dissipates divided by the ideal heat it would dissipate if the whole fin surface was at the base temperature. Long, thin fins might have quite low efficiency. There's a diminishing return.
Makes sense. Okay, so increasing S with fins helps, but with limits. What about the other lever? Increasing H, the heat transfer coefficient. This feels more complex. Fluid dynamics.
It is complex. Fluid flow can be chaotic, depends on geometry, fluid properties, velocity. It's messy.
So how do engineers get a predictive handle on H without testing every single possibility?
We use dimensionless parameters. These are clever ratios that group variables together and make experimental results more universal. They capture the essence of the physics.
Okay, like what? What's the key one for H?
The most important one for quantifying convective heat transfer is the Nusselt number.
Nusselt number, no town. What's it telling us physically?
Meltdown is essentially the ratio of heat transfer by convection compared to what you'd get by just pure conduction through the fluid layer right next to the surface.
So high Nernebein's convection is really working well, boosting heat transfer beyond simple conduction.
Exactly. The formula is Nu equals H times L divided by K sub FL, where L is a characteristic length and K sub FL is the fluid's thermal conductivity. We often use correlations to find neutral based on how the fluid is flowing.
Which brings us to how the fluid is flowing. That's the Reynolds number, isn't it?
See, absolute classic. Yes.
Yeah.
This line tells you about the flow regime. It compares the inertial forces, the tendency of the fluid to keep moving, to the viscous forces, the internal friction slowing it down.
And the formula.
RE equals rho times V times L divided by mu. Rho is density, V is velocity, L is that characteristic length again, and mu is the dynamic viscosity.
And the outcome. What does Torello predict?
It predicts whether the flow is smooth and orderly laminar or chaotic and mixed turbulent. Low true dollars is laminar, high true dollars is turbulent.
And for cooling, we generally want...
Often, we want turbulent flow because all that mixing brings cooler fluid constantly to the surface, which dramatically increases H and therefore nodal.
But turbulence sounds like it would need more energy to create, more pressure drop.
Absolutely. That's the crucial trade-off. Turbulent flow gives you much better heat transfer, but you pay for it with significantly higher friction losses. This means you need a more powerful fan or pump, using more energy, making more noise.
So engineers aren't just blindly chasing the highest possible turbulence.
No, not at all. Good design finds the sweet spot. Often just getting into the turbulent regime gives a big boost, but pushing $2 higher and higher might give diminishing returns on heat transfer, while the pumping power cost skyrockets. It's always an optimization game.
Okay, one more dimensionless number you mentioned earlier. For systems without fans or pumps.
Ah, yes. Natural convection, where the fluid moves purely because heating makes it less dense and buoyant. That's governed by the Rayleigh number, $1.
So new, $3, so new dollars.
Yeah.
These are the tools for predicting H.
They are essential. They let us use established correlations from experiments to predict performance for new designs.
So if natural convection isn't enough, which it often isn't for, say, high-power processors, we need forced convection. We need fans for air, pumps for liquids. How do we choose the right one?
Okay, now we bridge from thermal and fluid physics to system hardware. The first step is figuring out what the system demands from the fluid mover.
Meaning how much fluid needs to flow and how hard the machine needs to push it?
Exactly. We need the required flow rate, Q, and the total pressure increase or developed head, H sub P, that the pump or fan needs to provide.
And how do we calculate that required head, HEP-to?
It comes from an energy balance on the fluid circuit. You start with something like the Bernoulli equation, but you have to add terms for all the energy losses.
Losses due to friction in pipes, bends, going through the heat sink itself.
Precisely. We often use the Darcy-Weisbach equation or similar methods to calculate those frictional head losses. They typically depend on the square of the flow rate.
So the faster you try to push the fluid, the resistance goes up sharply.
Yes. And when you plot the total head required by the system versus the flow rate, Q, you get the system head curve.
The system head curve, what does that usually look like?
It's generally a curve that starts at some value, representing any static head difference, and rises roughly parabolically. So H required equals some constant K sub 1 plus another constant K sub 2 times Q squared.
Okay, so we know the point on that curve where we want to operate our desired Q and corresponding H. Now, how do we pick a machine that can deliver that efficiently?
The key classifying parameter, the sort of figure of merit for rotating fluid machines, is specific speed, N sub S.
Specific speed, N sub, that sounds important. What is it?
It's a non-dimensional number that relates the machine's optimal operating point, its speed, flow, and head, to its impeller geometry. It tells you what type of machine is best suited for a given job.
And the formula.
N sub S equals N times Q to the power of 0.5, all divided by H to the power of 0.75. N is the rotational speed.
Okay, what does a high Wunderkalle value mean versus a low one? Is there a rule of thumb?
Definitely. High nets machines are good for high flow rates, but low head requirements. Think axial flow fans, like a desk fan or a propeller. They move a lot of air, but don't build up much pressure.
And low nets.
Low nets machines are designed for high head, meaning high pressure, but lower flow rates. These are typically centrifugal pumps or fans with more complex impeller shapes designed to really throw the fluid outwards and build pressure.
So calculating the required Q and H, then finding the next out, guides you to the right type of fan or pump.
It's an incredibly powerful selection tool. Gets you in the right ballpark immediately.
But for liquid systems, especially pumps, there's a critical check we absolutely cannot ignore, right? Something about boiling.
Yes. Net positive suction head, or NPSH. This is non-negotiable. It's about preventing cavitation.
Cavitation? That sounds bad.
It is. If the pressure at the pump inlet drops too low below the liquid's vapor pressure at that temperature, the liquid will locally boil, forming vapor bubbles.
Okay, bubbles form. Then what?
Then, as those bubbles are swept into the higher pressure regions inside the pump impeller, they collapse violently, implode.
And that causes damage.
Major damage. It sounds like gravel is going through the pump, it erodes the impeller material, and drastically reduces performance. It can destroy a pump quickly.
So how do we prevent it? What's the check?
We compare two values. First is NPSH available, or NPSHA1. This is determined by your system. The static liquid level, the tank pressure, friction losses in the suction pipe. It's the absolute pressure margin above vapor pressure that your system provides at the pump inlet.
Okay, that's what the system gives you.
Right. Then you compare it to NPSH required, or NPSHR1. This is a property of the pump itself, determined by its design and provided by the manufacturer. It's the minimum pressure margin the pump needs at its inlet to operate without cavitating.
And the rule is simple.
Absolutely simple and absolutely critical. NPSHA must be greater than NPSHR1, usually with some safety margin. If it's not, you need to redesign the system inlet, lower the pump, or choose a different pump with a lower NPSHR.
All right, we've selected our pump or fan. It's installed. But systems don't always need to run at full blast. How do we control the output efficiently? You mentioned those system curves.
Yes, and this is where understanding the pump or fan laws, sometimes called affinity laws, becomes incredibly useful, especially for saving energy.
These laws tell us how performance changes if we just change the speed.
Exactly. Assuming we keep the same machine, same impeller diameter, and just change the rotational speed, N, the relationships are quite elegant.
Okay, what are they?
Flow rate, Q, is directly proportional to speed, N, so half the speed, half the flow.
Simple enough. What about the pressure, the head?
Head, H, is proportional to N squared. Half the speed, 1/4 the head.
N square. Okay. And the power needed to run it. That must be the important one for costs.
That's the kicker. Power, P, is proportional to N cubed.
Cubed. Wow. So even a small reduction in speed gives a huge power saving.
Massive. If you reduce speed by just 20% to 0.8 N, the power drops to 0.8 cubed, which is only about 51% of the original power.
Yeah.
You save almost half the energy.
That explains the big push towards variable speed drives, VSDs, doesn't it? Instead of the old way.
Absolutely. The old way was often throttling. You'd install a pump size for the maximum possible demand, and when you needed less flow, you just close the valve partway.
Which just wastes energy, right? Forcing the pump to work hard against an artificial restriction.
Exactly. It's like driving your car with the accelerator pushed down and controlling speed with the brake. Hugely inefficient. VSDs instead just slow the pump or fan down electronically.
So the machine's performance curve shifts down to meet the system curve at the lower required flow rate, naturally.
Precisely. And because of that n-cubed relationship for power, the energy savings are enormous. We're talking millions of kilowatt hours per year in large industrial or HVAC systems. It's a major factor in energy conservation.
Okay, shifting gears slightly, we focused on traditional mechanical cooling. Does the source material mention any alternative, perhaps solid-state methods?
Yes, briefly. It brings up thermoelectric coolers, or TECs.
Techs, how do they work? No moving parts.
Correct. They use the Peltier effect. It's a phenomenon where passing an electrical current through a junction of two different semiconductor materials causes one side of the junction to absorb heat, get cold, and the other side to release heat, get hot.
Like a tiny solid-state heat pump.
That's a perfect description. They're used for spot cooling, niche applications, or where reliability and lack of vibration are paramount, even if efficiency isn't always the best.
And how is their performance measured? Is there a figure of merit, like a null or dollars for pumps?
There is. It's called the figure of merit, usually denoted by Z.
ZZ. What defines it?
The formula is Z equals alpha squared divided by the product of rho and K.
Okay, let's unpack that. Alpha.
Alpha is the Seebeck coefficient, related to the voltage generated by a temperature difference. It's linked to the Peltier effect. Rho is the electrical resistivity of the materials.
And K is the overall thermal conductance of the device structure.
Right. So to get a good tech, you want materials with a high Seebeck coefficient, low electrical resistance, so you don't generate too much internal heat from the current, and low thermal conductivity, so heat doesn't leak back from the hot side to the cold side. It's a material science challenge.
Wow. Okay, we've really covered the whole chain then. From the heat starting in the silicon,
Battling through conduction resistance, the tricky threading and interface resistances.
needing to overcome the convective resistance to get into the fluid, using our understanding of muon and Newell dollars.
Which then dictates the need for a specific pump or fan, chosen using specific speed, and checked for safety with NPSA check.
And finally, operated efficiently using VSDs thanks to those n-cubed power laws. It all links together.
It really does. The whole process is a network, a series of resistances from the junction right out to the ambient air or water.
So maybe a final thought for our listeners, something to really chew on.
I think it's this. Because it is a chain of resistances, R dollars being the total, simply improving one part in isolation might not help much if it wasn't the bottleneck.
You mean like putting a massively powerful fan on a heatsink with terrible contact resistance at its base?
Exactly. The fan might lower the convective resistance dramatically, but if the contact resistance retrocetal was already huge and limiting the heat flow to the fins, the overall improvement, R dollars, might be tiny.
So the real art is identifying the largest resistance in the path, the bottleneck, and focusing your engineering effort there.
That's where you get the most bang for your buck. Balancing all the resistances from the microscopic interface right up to the fan selection is what leads to truly efficient and effective thermal design. It's a system problem.
Until the next equation design junkies, we are mechanical engineering made simple.